Now it's time to look at capacitors in AC circuits and see how they behave. But before we do that, let's recall what happens in the DC case. Okay, so if I have a battery and a capacitor, and let's say the capacitor is initially uncharged, I flip a switch, almost immediately I'm going to have the plates charged, pardon me, and Kirchhoff's loop rule states that the potential across the battery minus the potential across the capacitor must equal zero. And um, what that means is instantaneously the potential across the capacitor must equal the potential across the battery. And remember what happens with things like the current, okay? Um, the current is exponentially decaying until the plates are completely charged, at which point the current dies down to zero. The charge across the plates uh, is increasing. Whoops. As is the voltage across the capacitor. Okay. So these are all exponentials, right? In some form. These are all exponentials. But what about when I have a capacitor in series with an AC source? Okay. So obviously, if my voltage is sinusoidal, at some times the current is going to flow this way, and other times the current is going to flow this way. It's just going to bounce sinusoidally. But how can we analyze this? Okay. Well, so to start, remember once again that the voltage of your source minus the voltage across the plates must satisfy Kirchhoff's loop rule, and therefore the voltage across the plates must equal the voltage of the source. Okay? So the voltage across the plates is in what we call in phase with the voltage of the source. Okay? So if I were to plot my source and the voltage across the plates, these would be nearly identical. They wouldn't be nearly identical. They would be identical. Okay. But what about the current in the circuit? Well, right at t equals 0, this is the time axis, by the way. Right at t equals 0, I don't have any charge on the plates. And so with no charge on the plates, it's the easiest for the current to be pushed. Okay? So, how can we analyze this? Well, remember that Q is equal to CV. So if this is the plates, then that would be the voltage across the capacitor, but that equals V naught sine omega t. So this is equal to C times V naught sine omega t. Okay? And remember that current is equal to the time derivative of that. So this equals C V naught omega cosine. So remember that cosine and sine are shifted by 180 degrees. Okay, so cosine is the same thing as sine plus 180, or not 180 but 90 degrees, right? So sine omega t plus pi over 2 is equal to cosine. Okay. So if I were to plot my current, then it would look something like this. Okay. And this is one period at these points. Okay. So your current starts at a maximum, I naught, and then will cosinusoidally vary while your potential sinusoidally varies. Okay. But notice that I can write my current like this. Okay. I can write my current like this, and ignoring the phase factor for the moment, right? Ignoring the phase factor for the moment, this harkens back to Ohm's law, right? This harkens back to Ohm's law. So remember what Ohm's law says. V equals IR, and I therefore is equal to V over R. Well, here I have I, and to within the phase factor here is V, right? So what that means is if I compare these two equations, okay, I compare this equation with this equation, and I can immediately see that there's an analog for the resistance lurking right here. 1 over my resistance is equal to C omega, or R is equal to 1 over C omega. Now, we don't call this resistance. What we call this is reactance. And we actually give it the symbol chi sub C. So your reactance acts like an AC resistor. Okay? Your reactance acts like an AC resistor. And it has units of ohms. So what that means is farads times radians per second is equal to ohms. Okay? 1 over farads times radians per second, actually, is equal to ohms. So, with that in mind, okay, this is a measure of, if I think of my RMS voltage and RMS current, then IRMS is equal to my RMS voltage divided by my, what we call capacitive reactance. Okay? So this chi sub C is my capacitive reactance. And it acts just like resistance does. Okay, it behaves like resistance, but because this is sinusoidal, or my signal is sinusoidal rather, and my reactance depends on omega, my reactance can change based on the properties of my circuit, not just the physical properties of my resistor. Whereas my resistance would be a set value over most temperature ranges. If the resistor got really hot, of course, the resistance could change. But over a wide range of temperatures, your resistance is fairly constant, and it's based on the material that the resistor is made out of. But here, your capacitive reactance explicitly depends on the angular frequency of your circuit. So if you can adjust your angular frequency, like if you're in charge of some sort of function generator, then you can control the amount of reactance that your capacitor will put into your circuit. Okay? And so there are two extreme cases. The first is when omega is much, much greater than 1. And the second is when omega is much, much less than 1. So let's look at this circuit. With a capacitor and an AC source under this condition. Okay? Under this condition, one over C omega, if omega is really, really large, then chi sub C is going to be very small. And if you think about it, that should make some sense, because if your current if your voltage and therefore your current are very rapidly oscillating between these directions, then that doesn't really give the plates very much time to be charged before they're discharging again. So they're just going to go from plus Q to minus Q and vice versa on the other plate very, very rapidly. Okay, so the charge is just like bouncing back and forth. It's just being thrown around very, very rapidly. And that's not entirely different than just having an AC source with a wire. The charge is just going to bounce back and forth very, very rapidly. So this is basically kind of like no reactance at all. In truth, it's just very little reactance, but it's very little. Okay, it's hardly there for large enough omega. Okay, your charge is just going to bounce back and forth off of the plates. Your plates aren't really going to have time to have any of this exponential behavior that we had over here if the charge and discharge is happening very, very, very rapidly. So it's almost like your capacitor isn't even there. It's almost like your circuit doesn't even know that a capacitor is present. But in the other case, if your reactance is very, or if your omega is very small, then because omega is in the denominator, that means that your reactance is very large. Okay, and let's see why. So if I have a capacitor hooked up to a AC source, and my AC source is very, very small in terms of its angular frequency, what this means is that okay, so let me back up. Let's draw a diagram for my voltage when omega is very large. This is like this, right? Very, very rapid. But for small omega, that means your signal is very, 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 very stretched out. And it'll continue down, right? And then the wave will complete. Now, this isn't a very great picture, but you'll get the idea, okay? So what this means is over a finite stretch of time, this is very approximately constant. And if Vs is constant, then this exhibits a near DC behavior. And therefore, as the plates charge, your current decreases. Like if I look at my current over these same two times, then it will exponentially decay, at least approach exponential decay. And once it reaches the point where the plates are completely charged, your current has died out. And your current no longer flows. And therefore, if your current isn't flowing, your reactance is nearly infinite. Okay? So, when you have a capacitor in an AC circuit and you only have a capacitor, then your current will lead your potential across the plates by 90 degrees via these two relationships. Okay? So that's the first thing to note. The second thing to note is that your capacitor, coupled with whatever angular frequency is in the circuit, will act like a resistor. Okay? But we don't call it resistance, we call it reactance. And the two extreme cases where you can have really, really low omega or really, really high omega. In the really high omega case, the reactance is extremely small. It's like the capacitor is almost not even there. And in the very, very small omega case, then you have a nearly infinite reactance. And so this acts like a very, very high value resistor. Okay? So if you can tune your circuit properly, you can achieve a reactance of whatever you would like just by turning the dial on your angular frequency values. Okay? So one last thing to note, if we kind of draw a diagram for, now we're going to let this be at t equals 0. And I let my voltage across the capacitor be represented here, and my current through the circuit therefore is going to lead that by 90 degrees. Okay? Then this system, as time goes, okay, this system is going to rotate And eventually, the current, the potential will be completely reversed in the opposite direction. And my current in that case will be flowing in the opposite direction. Okay? So this is a precursor to what we call the phasor diagrams. And phasor diagrams are a way to look at how voltages and currents are related to each other. In the capacitor case, they are separated by 90 degrees. They will always be 90 degrees. And the current will lead the voltage when you have a capacitor hooked up to an AC source. Okay? So there is your capacitors in AC circuits.